Hello students, welcome back. Previously, we defined the primitive roots, or more precisely speaking, a primitive root of unity modulo m, and we went through its most important property. Any integer is uniquely congruent to a to the a certain power, mod m, where the power is selected from 0 to phi of m minus 1. So there are precisely phi of m choices, a to the 0 power, first power, second power, up to phi of m minus 1 power. Did I say any integer? Actually, I forgot this. Any integer that is relatively prime to m is uniquely congruent to a certain a to the r power, where r is from 0 to phi of m minus 1. There you go. Now from there, let's have a corollary. Let a be a primitive root of m. Oh, excuse me, sorry about the typo. Okay, let a be a primitive root of m. Then a to the h power is a primitive root of m if and only if the greatest common divisor phi of m and h is 1. Well, how do you get that? Well, we went through a certain property associated to GCD in section 1, and that's going to help. As for the proof, I left it as an exercise for you. It's not too difficult, but it's a nice exercise as a matter of fact. So you have to see that a is primitive root of m, so the order of a modulo m is just phi of m, and then how about order of a to the h power modulo m? And it's okay, all right, I'm giving away a bit too much. There's only one property associated to GCD in section 1, so you know what to do. Okay, once you get it done, assuming you got it done, then you're coming up with the next property here. How many positive integers are there from 0 to phi of m that is relatively prime to phi of m? They are phi of m. So there you go. Among those 0 to phi of m minus 1 here, not all of them will satisfy this, the GCD property. How many? Phi of m. So they are phi of m incongruent primitive roots of m, if there is one to begin with. Is that clear? If that is not really clear, then maybe I can leave that as an exercise as well. Okay, in any case, remember, there are phi of m incongruent primitive roots of m, if there's one to begin with. And when do we actually have one? So that we have indeed phi of m incongruent primitive roots. Well, good question. The big answer is right here. A primitive root of m exists if and only if. Yeah, it's if and only if, so we characterize completely. And m is 1, 2, 4, so far so good. P to the k power, or 2p to the k power, where p is an odd prime. That completely characterizes everything. It's by Gauss, but we can't prove it here. It's too hard. So in this course, we will prove only for the special case where m is a prime number. So m is 2, and then just p to the first power only up to that. As for special case, when m is 1, that's trivial, so I'll leave that to you. M is 4, okay, that 2 is easy, so I'll leave that to you. But in general, we'll prove only up to m is prime. So for all prime numbers, primitive roots exist. Consequently, we get phi of p. And what is phi of p? So phi of, let's see, phi of p is p minus 1 because p is prime. And yeah, that's it. There are this many incongruent primitive roots of prime number. But of course, even that requires a lot of preparation. So we're going to do it later in 3.4. This one here, Gauss theorem, I just want to show you the final result. We're not going to do all those. Well, before doing any of those, let's have some exercises. Okay, find a primitive root of the given integer. M is 9. Let's see. Before starting, let's find what is phi of 9. Phi of 9, let's see, among all positive integers from 1 through 9 that are relatively prime to 9, we have 6 of them. And the phi of 6, among all positive integers from 1 through 6, only 2 of them are relatively prime to 6. So phi of 9 is 2, so we expect 2 primitive roots if there is one to begin with. See the idea? Okay, and then how do I find one? Well, what choice do you have? 2 to the first power is 2, to the second power is 4. I mean, starting from 1 to whatever power is 2 bits, so starting from 2 is next easiest. Third power, fourth power, fifth power, oh, we ended up with p to the sixth power is 1. We got back, and everything here is all different. So, well, we were lucky. We got it through even in the first try. So we got it. Now how about 3? No, 3 doesn't appear here, so that's hopeless. And then, well, all the other numbers. Good luck. And then it turns out we're going to get to 5. So, some brute force computation, but this time we were lucky. There were 2 of them, and then the first one hit the bullseye. As a matter of fact, 2 squared showed up here as an intermediate step here. So you can see 4 is also out. And then you have 5. So first, alright, we have got lucky. And this one is out because it appears in the intermediate step here. Excuse me, I said it wrong. It doesn't always mean intermediate steps are wrong. 2 divides 6. That's why. And then 5. You don't have to bother 7 and 9 because we know they're only 2. How about m is 10? Well, again, go ahead with phi of 10. Remember, phi of m. So phi of 10, among all the positive integers, 1 to 10, only these are relatively prime to 10. So we have 4, and phi of 4 is 2. Among all positive integers, 1 through 4, only 1 and 3 are relatively prime to 4. So we expect 2 primitive roots modulo 10 if there's one to begin with. And then let's try. Starting from 1, that never works. Starting from 2, it'll fail. Oh, no, excuse me. 2 is already not relative prime with 10, so 2 is out of question. We start from 3, and we got lucky again. 3 hit. 3 squared, and third power, fourth power, back there. And the next one, 7, worked. And then as for 9, there's no reason to try because phi of 10 is 2, and then we have 2 primitive roots already, so there's no more. But another thing is 7 squared is 9, 9 already showed up. Oh, 3 squared is also 9, also showed up. So 9 to the second power is going to be fourth power, going back to 1, so that's not primitive. How about the next example? M is 15. Well, let's count first. Phi of 15. So phi of 15 is, let's see, among all positive integers from 1 to 15, only these are relatively prime to 15. Do you agree? And then what is phi of 8? Among all positive integers, 1 through 8, among those, only these are relatively prime to 8. So we have 4. So phi of 15 is 4. So we expect 4 primitive roots if there's 1 to begin with. So as usual, 1, that's never the case. Start from 2, and then 4, 7, etc., etc. But if you try, you're never going to get any 1. 2 to the first power is 2, second power is 4, third power is 8, fourth power back to 1. 4 to the first power, second power, back to 1. 7 to the first power, second power, third power, and fourth power is back to 1. You're not going to get anything to 8th power. 8 to the fourth power coming back to 1 already. 11 to the second power is back to 1. 13, again, fourth power comes down to 1, and 14 to the second power comes down to 1. So there is no primitive root. This thing can happen. If you have a prime number, then always there is a primitive root. But for other numbers, no. As a matter of fact, we are not going to prove it, but it may be a good idea to remember this result. In order to have a primitive root, m should be 1 to 4, or p to the k power for an odd prime, or 2p to the k power for an odd prime. So what did you have before? 3 times 5? No, that didn't work. Previously, what did you have? This one, 2 times 5. So yeah, it fell into this, so it worked. This one, 3 squared, so it fell into this category, so it worked. So primitive roots, some brute force computation, we did. Well, I didn't actually do anything, I just show you the computation. Next, do we have enough time for 2.4? Fermat numbers? Probably not. Let's stop here. We're going to come back and discuss that Fermat number in a separate video, and it's likely to be a short one. And then after that we may add a little bit more, maybe or maybe not.